This video is for the revision of buffers, HL. So what's a buffer? In your notes, you'll see that buffer is a solution whose pH remain unchanged if you add a little bit of acid or a little bit of base in it. Even if you dilute it, the pH remains almost unchanged. So that's a buffer. How do we make a buffer? A buffer solution is, so if we have a weak acid and the salt of that weak acid. So for example, ethanoic acid and the salt of ethanoic acid. Okay, if we were to put in 50-50 ratio here in moles, so their concentration would be the same. That would give us the best buffer. And besides a weak acid, we can also do the same for a weak base. So NH3 and NH4 plus Cl minus. So weak base and its salt. Same thing here, the ratio should be 50-50. And that would make the best buffer. It doesn't have to be exactly 50-50. We can still make a buffer, but the best buffer would be the one that is 50-50. Okay, let's see why. A weak acid would dissociate like this. So I'm going to use ethanoic acid as my example. So it dissociates to CH3COO minus plus H plus. And also there's a salt. This will dissociate fully. So in my buffer, what is still available? This has dissociated fully. So only this and Na is available in the final buffer. But as for the weak acid, this is still available because it's reversible. So which means in my buffer just now, there would be CH3COOH, there would be CH3COO minus, there's some Na plus, there is some H plus, but there is no CH3COONA anymore because it has dissociated. So these are all available in my buffer solution after mixing them together. Okay, but if you look at these two equations that I wrote up here, you'll see that since this is a reversible arrow, so most of the CH3COO minus would have came from the salt. So this value would be so little that it's negligible when compared to this amount. So when I want the amount for this CH3COO minus, I would say that I can get it from my original salt. And as for the weak acid, since it dissociated so little, I can say that the concentration is almost as the original CH3COOH. Okay, so since the salt dissociated fully, so there's no calculation about Ka here, but then this is a weak acid, so there is a Ka for that. We already covered that Ka equals to the product, which is the H plus, the CH3COO minus, over the CH3COOH here. So when I take the value, the H plus comes from this. The salt or the CH3COO minus, we will take from the original salt concentration because all of it has dissociated to CH3COO minus. Okay, I'm sure you would think that, okay, it should be CH3COOH from the salt plus the one that dissociated from the weak acid. But the one that dissociated from the weak acid is so little that it's negligible when compared to the amount from the salt. So I'm just going to take the concentration from the salt. And since the weak acid dissociated so little, so when we want this value at equilibrium, we're just going to take the concentration of the initial acid, knowing that the dissociation is so little, a lot of it is still CH3COOH. So these were the assumptions that we make. So if I turn the equation around, I want the H plus. That's the calculate pH, right? So I want the H plus. I'm going to bring everything over to the other side. So that's Ka multiply acid, the concentration of acid, over the concentration of salt. So I brought everything to the other side because I just want the H plus to calculate my pH later. Okay, so if I negative log all of this, so it will turn to this equation. Negative log of H, that will be pH, equals to, so since negative log Ka, so this is pKa, and plus negative log of acid over salt. So that came from here. So that's how I get the equation pH equals to pKa plus log salt over acid. So I changed this and make this a plus. So you can leave the minus there, that's fine also. So if you'd like, it can be pH equals to pKa minus log acid over salt. That works as well. Okay, similarly, the same way is derived for POH, except that we're using Kb and also log salt over base. Okay, so the equation that plays the main role in buffer is the one that has a reversible arrow. So it's going to balance the amount of H plus. So if the amount of H plus or the concentration of H plus is not much changed, then the pH won't change a lot, so by a very little bit. So this equation is very important in playing its role in the buffer solution. Okay, salt is fully ionized, so this CH3COO minus and Na plus is not going to reverse to become this. So this equation is only to provide the CH3COO minus. That's an important role in this buffer solution. Okay, so when an acid is added, so acid would be H plus, and when a base is added would be OH minus. Always focus your eyes on this equation. So when acid is added, this ion is going to help balance it out. So the concentration of H plus is not disturbed, so the pH is unchanged. Okay, when a base is added, then we take this one. So again, the OH is not disturbed. If the OH is not disturbed, then the H plus won't be disturbed. Therefore, the pH is unchanged. Let's do the same for a weak base buffer. So weak base buffer is made by, in this example, ammonia and also its salt. Again, its salt is going to ionize fully to the ions. So NH4 plus and Cl minus will be in there. So in my buffer, I would still have ammonia, NH4 plus, Cl minus, OH, but I will not have NH4Cl. Again, the main role of the salt is to provide the NH4 plus. So the amount of NH4 plus actually came from how much of NH4Cl that we added in. So the moles all came from here. So this gives the concentration of the NH4 plus, not from the weak base equation, because this amount is so little, it's negligible. We're taking the value from here. And since this dissociated so little, so we can take the value from here itself. Okay, so let's see what happens when acid is added and when a base is added. Again, focus on this equation because it's the one that's reversible. This one is not going to go back. It's not going to balance anything. So this equation is your focus when you want to balance the pH, because OH is going to affect the pH. So if the OH concentration is balanced and stable, so then the pH will not change. So when an acid is added, I'm going to take this, and it will form more NH4 plus. So there's no change in H. If there's no change in H plus concentration, then there's no change in pH. Okay, when a base is added, then this one is going to help balance it out. So an extra OH it's supposed to disturb the pH, but since it's balanced out by NH4 plus, it's going to form more ammonia and water, so the pH remains unchanged. Let's have a look at an IB question. A buffer solution can be made by mixing ammonia with ammonium chloride. We just saw that just now. So to make this, sometimes we'll do a titration. And in this case, they're going to put HCl here and ammonia inside here. First question is not about buffer. They just want the pOH of a solution of 0.125 mole per dm cube of ammonia. So we're just going to use this Kb equals to OH squared over the concentration. So you have the pKb here, so you'll need to calculate the Kb from that. So put the Kb value here. Equals to the OH squared over the concentration, which is 0.125. Okay, so I'm going to jump straight to the answer. pOH equals to 2.83. Okay, somewhere here you will get that the concentration of OH is 1.49. So negative log that, you will get this. The next part is about buffer. So let's see, let's put in the values for the question. It says here, there's 12.5 centimeter cubes of hydrochloric acid that is run from this burette. So the concentration is the same. The concentration of ammonia is also 0.125. But there is 25 centimeter cubes of it. And we are only going to run 12.5 centimeter cubes of HCl from the burette. Okay, so the mixture, what's the mixture going to contain? So we have ammonia plus HCl. We're going to get the salt. And we have 25 centimeter cubes. They have the same concentration, so I'm treating the volume as if it's mole already. The mole ratio is the same here. So there's 12.5 centimeter cubes, so which means only 12.5 of the ammonia has reacted, leaving another 12.5 behind. So in my mixture, I have 12.5 centimeter cubes of ammonia, and the HCl reacted with the ammonia and became 12.5 centimeter cubes of salt. We're going to use this formula. So pOH equals to pKb is already given up here. So 4.75 plus log. So they have the same volume, therefore they started off with the same concentration as well. So therefore their concentration is now the same. So cut, log 1 is 0. So the POH, so log 1, anytime you have the same value here, it will be log 1. Log 1 is always 0, so 4.75. So what's my pH then? Just take 14 minus that. And I have the answer here, 9.25. Now, going back to the curve that we saw the other day, so within this curve, there's actually a buffer. So a buffer is 50% salt and 50% the weak one. So here, there's the weak base. So where's the weak base? The weak base would be at 50 centimeter cubes here. That is 100% of weak base. And in the middle here, 25 centimeter cubes of alkali, that would be 100% of salt. So if this is the 100% of salt, and this is 100% of weak base, so right in the middle, that would give me my buffer region. So at this point, the concentration of the salt and the weak base is the same, so pKb will be equal to POH. Similarly, for weak acids, so here is 100% of weak acid, and at this point is 100% of salt. So right in the middle, 12.5. This will be my perfect buffer where there is 50% of weak acid and 50% of the salt of it. So this we call the buffer region, and this in the middle is the perfect buffer where you have 50-50. So at that point, pKa equals to pH.